The wind cut across the airfield at Boscombe down like a blade, dry, cold, relentless. In the half-light of dawn, the concrete shimmered with frost. Ground crews moved in silence, collars high, breath ghosting in the pale air. At the far end of the runway, a lone aircraft stood poised, a prototype unlike any other. Its nose gleamed with the sheen of new metal, its propellers to sets, turning in opposite directions, a vision of mechanical defiance. Inside the cockpit, the test pilot adjusted his harness, watching the instrument needles tremble. He knew what waited above the clouds, the German Me 262. Faster, higher, seemingly untouchable. Against such machines, the age of the propeller appeared over, but somewhere behind this new design was a single mind, a British engineer who refused to accept that verdict. The engines roared to life, scattering the frost in spirals of white vapor. The aircraft began its run, gathering speed, not to chase the jet, but to prove that Britain's piston power could still fight the future. By the winter of 1944, the balance of air power over Europe was shifting. The Allies held the skies in numbers, but Germany, desperate and cornered, had unleashed a new kind of weapon, the jet fighter. The Messerschmitt Me 262, sleek and silver, tore through bomber formations at speeds no propeller-driven aircraft could match. RAF pilots who once hunted the Luftwaffe now found themselves outpaced, outclimbed, and, for the first time in years, uncertain of the outcome. Reports reached fighter command through scattered reconnaissance and combat accounts. Gun camera footage. We showed brief flashes of a new silhouette, swept wings, twin engines, vanishing in seconds. At Bentley Priory, analysts examined every frame, calculating performance from fleeting glimpses. By early 1945, they estimated a top speed near 540 miles per hour, a full 100 faster than the Spitfire 14 or Tempest V, the pride of Britain's piston age. The challenge was immediate and existential. Jet propulsion was still in its infancy in Britain. The Gloucester Meteor, though operational, was restricted to home defense and plagued with engine shortages. The RAF's striking arm over Europe still depended entirely on piston power. And yet, across the Channel, the Luftwaffe's jet units, small but lethal, threatened to erode the hard-won Allied advantage in Whitehall. The Air Ministry faced an uncomfortable truth. It would take months, perhaps years, for jet aircraft production to meet operational demand. Britain needed an interim solution, something that could fly now, fight now, and survive against an enemy that had already stepped into the future. The question reached beyond tactics. It was an engineering dilemma: how to extract more speed, more thrust, more performance from the piston engine, a technology that had seemingly reached its limits. By late 1944, many designers considered the matter closed. A propeller, turning faster, simply lost efficiency. Beyond a certain point, its tips broke the sound barrier, tearing at the air with noise but no gain. Engineers called it drag nature's speed limit on the old world of blades and pistons, yet within that limitation lay the seed of an idea. Somewhere in the maze of Britain's wartime aviation industry in drafty design offices from Farnborough to Hatfield, from Kingston to Yeovil, a handful of designers refused to concede defeat. Among them was one man whose proposal would be dismissed by many as unworkable, impractical, even impossible. The proposal concerned the propeller itself. If the barrier was in how air was cut, not how fast it was driven, then perhaps the answer lay in counter-rotation to propellers turning in opposite directions on the same axis, cancelling each other's torque, and slicing the air with greater efficiency. The concept was not entirely new, but wartime Britain had neither the time nor resources to pursue radical re-engineering of aircraft drives. It was a problem of complexity, gearing, balance, vibration, cost. And yet, in the darkest months of the war, necessity forced reconsideration. The Air Ministry authorized a series of emergency studies at the Royal Aircraft Establishment, Farnborough, and the Ministry of Aircraft Production circulated requests for proposals. The call was clear: if Britain could not yet build enough jets, she must build faster propeller aircraft, and do so immediately. It was a moment of quiet crisis. Production lines at Castle Bromwich and Langley were already stretched. Skilled men were fighting, factories bombed, materials rationed. But within that constraint, the story of one designer and one aircraft began to take shape. A story not of theoretical advance, but of stubborn practicality, not of glory, but of resolve. For Britain's engineers, defeat was never an option. The enemy's jet might represent the future, but British hands still built the present, with precision, patience, and the quiet certainty that an answer, however improbable, could still be found. And in one workshop, that answer began to turn, not on paper, but in metal. In wartime Britain, design was as much a matter of endurance as invention. The nation's aircraft industry, vast, improvised, and overworked, was sustained by a lattice of small firms, subcontractors, and experimental units. Between them stood the Ministry, the Royal Aircraft Establishment at Farnborough, and a handful of chief designers whose reputations had grown alongside their machines. Every morning, trains carried engineers from bomb-damaged suburbs to the drawing offices of Hawker, Supermarine, de Havilland, Bristol, and Westland. They worked under blackout curtains, their drafting lamps the only light. Many were barely in their 30s, yet their calculations determined whether Britain's airmen lived or died. The war had turned design into an emergency science. At Farnborough, research teams tested every conceivable configuration of wing, propeller, and air intake. Wind tunnels roared day and night, their walls lined with frost where moisture froze in the high-speed airstreams. In these cramped cells of innovation, Britain's quiet revolution took place, one defined not by bold declarations but by patient, incremental discovery. Among the many challenges that reached the RAE's desks in late 1944 was the propeller problem. Engineers were now chasing fractions of efficiency, new alloys, thinner blades, altered pitch angles, but none of these measures could compensate for the growing gap between piston aircraft and the jet age. The traditional single-screw propeller produced too much torque, too much drag, and too little speed. It was within this context that a handful of designers proposed radical alternatives. One of them, a man of meticulous temperament and few words, worked for de Havilland Propellers, a subsidiary already stretched building air screws for Mosquitoes and Hornets. His name would later become synonymous with the idea that refused to die, the contra-rotating propeller. To the untrained eye, it appeared absurd: two sets of blades, spinning in opposite directions, fed by a single power shaft and a labyrinth of gears. But in aerodynamic terms, it solved three problems at once. It neutralized torque, increased thrust efficiency, and reduced slipstream losses. In short, it allowed the piston engine to do more with the power it already had. The concept, however, came at a cost. The gearing required to synchronize opposing rotations was intricate and heavy. Manufacturing tolerances were brutal. Fractions of a millimeter separated stability from destruction. If the balance failed, the entire mechanism could tear itself apart within seconds. Many within the ministry considered it a curiosity at best, too complex for wartime production, too delicate for frontline service. But others saw promise. The Royal Navy's Fleet Air Arm, facing jet threats to its carriers, pressed for rapid trials. They understood that a naval fighter, lighter, more compact, and with limited runway length, might benefit most from the extra thrust of a contra-rotating system. The ministry approved prototype development under strict secrecy. In early 1945, one of the first test beds, a heavily modified Seafire, arrived at Farnborough. Meanwhile, across the airfields of southern England, jet sightings were increasing. RAF Tempests scrambled to intercept, but the Me-262s vanished before contact. Frustration grew. Pilots returned with reports of ghosts in the sky. The need for a countermeasure became urgent. By spring, the problem had coalesced into a single challenge. Could Britain's last generation of piston aircraft, led by designs like the de Havilland Hornet and Spiteful, achieve jet-like speed through propeller innovation alone? The RAE's findings suggested it was possible, but only just. Gains of 20 to 30 miles per hour might be extracted with improved blade geometry, and another 10 or 15 from control. Enough, perhaps, to level the odds in a chase or escape. It was a gamble worth taking. By mid-1945, as the Allies advanced through Germany, test pilots at Boscombe Down and Farnborough began pushing the limits of these experimental aircraft. Among them were men who had fought in the Battle of Britain, now lending their experience to the last act of a dying technology. The piston engine, though nearing its twilight, had not yet conceded defeat. For Britain's aviation community, this was not merely a technical pursuit, it was a statement of identity. To innovate under constraint, to solve with what remained at hand, was the essence of wartime endurance. And so, in those final months, as jet exhausts roared over collapsing Germany, a quieter sound persisted in the hangars of southern England. The hum of gears, the turning of blades, the faint promise that one more idea might still make the difference. That idea, dismissed by many, perfected by few, was about to prove itself in flight. He was not a household name, nor a man of speeches. To his colleagues at de Havilland Propellers, he was simply the designer who refused the easy answer. Educated before the war in the quiet rigor of Cambridge engineering, he belonged to that generation of British innovators who regarded invention as duty, not glory. In meetings he spoke rarely, sketching instead arcs, gear trains, torque diagrams, the language of function. When others saw futility in propeller research, he saw imbalance, inefficiency, and the chance to correct both. In 1944, while London burned under the final V-weapon raids, he worked through nights at the company's Hatfield workshops, his papers held down by mugs of cold tea. His proposal for a contra-rotating airscrew was met first with silence, then with polite doubt. Yet he persisted, submitting detailed calculations to the Ministry of Aircraft Production. The first prototype gearbox failed on the test stand within minutes, gears shearing under load. The second ran for 3 hours. The third, at last, held steady. In his log he noted, vibration within limits, efficiency gain confirmed. It was a sentence without fanfare, but in it lay the culmination of years of quiet obsession. He never sought recognition. To him, engineering was its own form of service, measured not in medals but in revolutions per minute. While design officers wrestled with equations, Fighter Command faced a dilemma of tactics. By late 1944, the Luftwaffe's jets had reduced interception to a matter of seconds. A Me-262 diving through a bomber stream could strike and vanish before escorting Spitfires had turned their guns. Radar operators at Bentley Priory logged blips that appeared and disappeared too fast to track. Pilots, accustomed to fighting in turning circles and altitude bands, found their training outdated overnight. The RAF's response was pragmatic: attack the jets on the ground. But this strategy, known as rat catching, relied on timing and intelligence, not air superiority. The psychological effect was profound. Aircrew spoke of chasing shadows. Victory felt uncertain, yet some officers saw opportunity. If the jet's greatest advantage was speed and level flight, their weakness was acceleration and maneuver. A propeller aircraft with immense low-speed thrust, capable of rapid climb and tight turn, could exploit that window. The new propeller designs promised exactly that, if they worked. Britain could field piston fighters that retained agility yet closed the speed gap. Within Fighter Command, the idea gained quiet support. Test reports from Boscombe Down suggested that the contra-rotating units reduced torque on takeoff, allowing more power to be applied without veer. That meant shorter runways, faster climbs, quicker interception. For a service stretched across hastily built airstrips in France and Belgium, this was more than theory, it was survival. At Farnborough, the experiments took on a rhythm of their own. Engineers spoke of the whispering props, a low, even tone unlike the familiar single-blade drone. The dual rotation cancelled vibration so effectively that instruments once blurred by resonance now read clearly. Test pilots described the sensation as uncanny, smoother, steadier, more precise. The first successful flights took place early in 1945. The test aircraft, a modified Seafire-15, lifted cleanly from the runway, climbed through low cloud, and returned without incident. Subsequent trials with the Havilland Hornet F1, purpose-built around the new system, it showed remarkable results, speeds exceeding 470 miles per hour at altitude, rival to early jets in level. Observers at Boscombe noted another advantage. Engine cooling improved under contra-rotation as slipstream turbulence was reduced. The RAE's report, filed in March 1945 and preserved at the National Archives, Aviaggio di 1544, stated, performance increased measurable and repeatable, pilot workload reduced, no adverse handling noted. To those who read it, the implications were clear. Britain had achieved, through mechanical refinement, what had seemed the preserve of the jet age: efficiency through precision rather than revolution. Outside the test fences, few knew of these trials. The war was reaching its end. Newspapers spoke of Berlin, not of propellers. But within the Ray's hangars, the sense of purpose remained electric. Each successful run felt like a small vindication, proof that intellect and patience could still outrun haste. And as the prototype Hornet sliced through the Hampshire sky on its final test circuit, observers realized they were watching the closing act of the propeller age, and perhaps its finest hour. In 1945, every advantage mattered. Air superiority was not just won in the sky, but forged in the laboratories of Britain's industrial heartland. The nation's aeronautical engineers worked with a kind of restraint, urgency, chasing fractions of performance that might mean the difference between life and death. The airscrew represented the outer edge of what piston technology could offer. To make two sets of blades spin in opposite directions required an intricate gearbox, concentric shafts driven by a single power unit. Inside, a series of planetary gears redistributed torque, each tooth machined to tolerances previously unthinkable in mass production. The work demanded not only skill but courage. One error in metallurgy could shear a shaft or lock the entire mechanism mid-flight. At de Havilland's Hatfield factory, machinists developed new techniques to harden gears against fatigue. Micrometers were recalibrated daily, and inspection teams worked under the quiet authority of the ministry's quality officers. Every successful unit that passed testing was a small miracle of precision, a reminder that Britain's strength lay not in abundance, but in mastery of detail. When the RAE's technical report concluded that efficiency gains exceeded 6%, modest on paper but decisive in combat, the news spread through design circles like a coded victory. It was proof that ingenuity, guided by discipline, could still find room in a war increasingly ruled by speed and flame. Behind the success of any innovation stood a chain of decisions, some cautious, others bold. In Whitehall, the Air Council weighed competing priorities: the media jet program, the continued production of Tempests and Spitfires, and the untested promise of the contra-rotating propeller. Every new project risked diverting resources from the front. The Minister of Aircraft Production, Sir Stafford Cripps, proved limited funding under the category experimental high-efficiency airscrew systems. His reasoning was pragmatic. If the idea failed, losses would be minimal. If it succeeded, the benefit would be immediate. Within the Air Ministry's labyrinth of committees, few remembered signing off the order that allowed one designer's experiment to proceed. Yet that single approval, buried in administrative routine, would produce one of the finest propeller aircraft ever built. At Boscombe Down, Air Vice Marshal Geoffrey Tuttle authorized live trials in operational conditions. He had seen too many promising designs shelved by peacetime caution. His instruction to the test pilots was characteristically brief. Find its limits. Those limits proved elusive. Each sortie revealed greater potential, better climb, steadier aim, fewer mechanical failures. By the summer of 1945, with Germany defeated and Japan still resisting, the ministry placed orders for production variants of the de Havilland Hornet. Leadership, in this case, had not been loud or visionary. It had been patient, methodical, and quietly brave. War demands invention, but it also exposes the morality of invention. For the men and women behind Britain's wartime aviation, innovation was not a race for supremacy but a responsibility, a means to save lives by shortening the fight. In that light, even a propeller became a moral instrument. Many who worked on the program did so anonymously. Draftsmen, typists, toolmakers, and inspectors each contributed to an idea they might never see in flight. For them, the victory was not personal. It lay in the knowledge that British pilots would return alive because the machine beneath them had been built to its best possible standard. The contra-rotating propeller embodied that ethic. It was neither glamorous nor revolutionary. It was, in essence, refinement elevated to art. Where the jet was a symbol of speed and modernity, the contra-rotor was a symbol of persistence. The refusal to abandon the proven in favor of the merely new. When news of the war's end reached Hatfield and Farnborough, production workers paused, not in celebration but in silence. They understood that peace would scatter them back into civilian life, that their wartime craft might soon be obsolete. Yet, among the test reports and drawings they left behind was something deeply human, the record of minds that had given their utmost to a cause defined not by conquest, but by endurance. Even in triumph there was restraint. One Ray engineer, writing in his final report to the ministry, summarized it best: the virtue of this design is not its novelty, but its precision. It is proof that progress can be achieved without abandoning principle. By the summer of 1945, Britain stood at a crossroads. The jet age had arrived, yet the last of her propeller aircraft, refined, efficient, and unmistakably British, still ruled the skies, and in their turning blades, one could hear not defiance, but the quiet echo of a nation's perseverance. The morning broke pale and cold. A thin frost lay across the Wiltshire fields, gleaming under a hesitant sun. On the tarmac stood a silver aircraft unlike any other in Britain's skies. The prototype de Havilland Hornet, its twin Merlin engines fitted with gleaming, contra-rotating propellers. The design team gathered behind the control hut, coats buttoned against the wind. Among them was the quiet figure of the designer, hat brim low, hands clasped behind his back. Months of calculation had led to this moment. If the gearing failed, the test aircraft could disintegrate before clearing the runway. If it held, Britain would have proven that piston technology still had more to give. At 7:32 hours, the twin Merlins fired. The sound was immediately different, not the deep, uneven rumble of ordinary engines, but a smooth, even note that seemed to hum through the frost. Observers noted the absence of torque swing. The aircraft rolled straight and true. The test pilot, squadron leader Eric Brown, eased the throttles forward. Within seconds, the Hornet surged down the runway, lifted cleanly, and climbed into the mist. For a minute, all that remained on the airfield was the faint echo of propeller wash and the smell of high-octane fuel. Inside the cockpit, Brown kept a steady hand. The Hornet responded instantly, balanced, precise, almost effortless. At 8,000 feet he leveled off, advanced the throttles, and watched the airspeed needle climb past 400, then 450 miles per hour. The engines held steady. No vibration, no shudder, no sign of strain. He banked gently to port, testing the turn. The aircraft obeyed without complaint. Then, pushing into a shallow dive, he reached a recorded 485 miles per hour, faster than any British piston aircraft had ever flown. Down below, the flight observers watched the speck of silver trace wide circles in the sky. The telemetry recorders clicked steadily. When Brown finally touched down 20 minutes later, he taxied into a silent crowd. Engineers leaned in, listening to the idling note, smooth as a turbine. He shut down the engines, opened the canopy, and climbed out, frost still clinging to the wing roots. His words were simple: no torque, no yaw, perfect balance. She'll climb like nothing else. The test director, a man rarely given to praise, allowed himself a nod. The data confirmed what instinct had already told them. The contra-rotating system had worked. The propeller, long dismissed as obsolete, had matched the jet in stability and acceleration. That afternoon, the team gathered in the small debriefing hut. The heater coughed in the corner. Pencils tapped on clipboards. Readings were read aloud: thrust output, engine temperature, fuel flow. Each figure, each line of ink, told a quiet story of vindication. After months of doubt, the numbers spoke plainly. Efficiency gained 6.4%. Climb rate increased 12%. Torque offset complete. At Farnborough, the Ray's senior aerodynamicist received the telegram: trial successful. Performance exceeds specification. Recommend production. He placed it carefully in his folder and simply wrote, History -20, March 1945. In Whitehall, the Air Ministry's Technical Development Board met 3 days later. Copies of the test report lay before them, stamped secret. The language was typically restrained. New airscrew system demonstrates substantial increase in effective thrust. Recommend immediate continuation of type. Yet behind those cautious words was quiet triumph. Within weeks, production orders were issued for the Hornet's first batch. De Havilland's engineers returned to Hatfield to oversee tooling and balance procedures. The war in Europe was nearing its end, but the work continued with undiminished purpose. Every unit assembled carried not just mechanical precision, but moral weight, the sense that this achievement, born of persistence, had arrived just in time to prove that faith in British engineering was never misplaced. In the months that followed, the Hornet would set new records. Fastest twin-piston aircraft in service, longest operational range, highest climb rate for its class. It was the swan song of an era, and yet its innovation, the contra-rotating airscrew, would outlive the piston itself. The system would later find its way into Britain's first generation of turboprops and naval aircraft, its design lineage still traceable to those frozen runways of 1945. But that day at Boscombe Down, none of that was yet known. The men watching from the hangar doors saw only the shimmering vapor over the wings and heard, for the first time, a sound that marked the closing of one age and the opening of another, two propellers turning in perfect opposition, a harmony of precision and defiance. And in that sound, the old world of flight bowed out, not defeated, but fulfilled. The news from Boscombe Down traveled quickly through Britain's closely knit aviation circles. Within a fortnight, a small notice reached the Ministry of Aircraft Production. Summarized in the concise, unemotional prose of bureaucracy, airscrew system approved for service use. No defects observed. But behind those words lay years of quiet persistence. A triumph achieved not by revolution, but by refinement. At Hatfield, engineers gathered around the prototype gearbox laid out on a steel bench. Each gear tooth was polished, each bearing checked for wear. These were not objects of beauty but of craft, symbols of Britain's industrial patience. Apprentices from nearby colleges were brought in to observe, their instructors telling them, this is the future, precision, not power. The future, in fact, was already here. By April 1945, the first production de Havilland Hornet F1 South rolled out for operational testing. Sleek, twin-engined, and fitted with those gleaming contra-rotating propellers, they represented the pinnacle of piston-powered flight. Test pilots recorded speeds of nearly 490 miles per hour, outpacing every Allied aircraft then in service except the Meteor jet. For Fighter Command, it was vindication. Britain had not merely caught up to German technology, it had surpassed it in efficiency. Where the Me 262 demanded delicate throttle management and devoured fuel, the Hornet offered range, reliability, and control. In the language of pilots, it flew clean. At Farnborough, the Ray compiled its final report. The cover sheet, dated May 1945, reads simply, airscrew, twin-engine application successful. Insider. The data was meticulous. Thrust coefficient graphs, torque cancellation curves, vibration frequency charts. Yet between the numbers was something less tangible. The story of a nation's refusal to yield to technological inevitability. The British had not invented the jet, but they had perfected the propeller. The Air Ministry authorized production for the Hornet F3 and C Hornet, designed for the Fleet Air Arm on carriers in the Channel and the Far East. Naval pilots trained with the new machines, marveling at their responsiveness. She answers like thought, one wrote in his log at RNA's Ford. For a generation raised on Seafires and Corsairs, the Hornet represented something almost mythical, the perfect aircraft at the very moment it was destined to become obsolete. As the war in Europe ended, the Hornet's true test came not against the Luftwaffe, but in the vast distances of the Pacific. Japan's surrender in August 1945 halted any chance of combat deployment. Yet by then, the aircraft's reputation was secure. The design's legacy would extend far beyond war. Its gearing principles were later adapted for the de Havilland Dove, the Avro Shackleton, and the Fairey Gannet, Britain's first successful turboprop naval aircraft. At the National Archives, a post-war memo captures the quiet pride of those involved. It reads, in conclusion, the performance achieved represents the final and highest development of the piston aircraft. It stands as evidence of what British engineering can accomplish under pressure. Even as jet engines roared into the post-war dawn, the men of Hatfield and Farnborough knew they had created a masterpiece of balance and efficiency. The culmination of half a century of aeronautical craft. The propeller, once dismissed as a relic, had ended its service at the very edge of the possible. For the designer, recognition came slowly. He declined public honors, preferring his workshop to the press. When approached by the Royal Aeronautical Society for a lecture, he spoke briefly, describing the work as a necessary exercise in precision. His audience, many of them younger engineers now devoted to jet turbines, listened with quiet respect. They understood what he meant. Progress was not a race, but a lineage. In later years, The Hornet would be remembered in the same breath as the Spitfire and Mosquito, the last of the great wooden aircraft, designed in a Britain that valued craftsmanship as much as power. Its smooth flight, its calm steadiness, and its twin, counter-turning blades embodied the British temperament in metal, measured, reliable, and endlessly patient. By the time the final Hornets were withdrawn from service in the early 1950s, the sound of contra-rotating blades had already faded from the skies. But those who had stood at Boscombe Down on that cold morning in 1945 would never forget it. The clear, even hum of perfect equilibrium, marking the end of an age not with noise, but with grace. And so, as the jet age dawned, Britain's last propeller fighter left its contrails over the English fields not in farewell, but in quiet triumph. By the summer of 1946, Britain's airfields were quiet again. The victory parades had ended, the blackouts were lifted, and the once urgent roar of Merlin engines was now an echo of a war already fading into history. Yet in hangars at Hatfield, Farnborough, and Boscombe Down, engineers continued their work. Their task was no longer survival, it was transition. The de Havilland Hornet, now entering limited squadron service, stood at the crossroads of two eras, sleek, narrow-winged, and almost absurdly fast for a piston aircraft. It was admired as a technical marvel and a relic at once. The Royal Air Force, still reconstituting after demobilization, faced an uneasy question. What place did propellers have in a jet-powered future? The government's 1946 White Paper on Defense offered a cautious answer. It recognized the Hornet as the ultimate realization of reciprocating engine design, yet confirmed that future investment shall be directed toward jet propulsion and axial flow research. The tone was respectful, almost elite. The Hornet was not dismissed, it was honored, then gently retired from policy relevance. At Farnborough, the Royal Aircraft Establishment archived its test reports. Engineers annotated the margins in pencil, recording minute details of air pressure and torque behavior. Those notes would later influence early turboprop designs. The Armstrong Siddeley Python and Rolls-Royce Dart among them. The principles of control rotation, vibration, balance, and aerodynamic efficiency lived on, quietly embedded within Britain's post-war design culture. For pilots, however, the Hornet remained a machine of legend. Squadron leader Maurice F. Wilkes, one of the first to test the production models, wrote in his log, "The Hornet feels alive, as though its wings anticipate movement before the mind does. It is the end of an era and the finest of it." That sentiment was shared across the service. Many who had flown Hurricanes and Spitfires during the Battle of Britain regarded the Hornet as the culmination of all that experience. Smoother, faster, cleaner. It represented not nostalgia, but fulfillment. At the same time, the jet prototypes emerging from Gloucester, de Havilland, and Hawker made the contrast unmistakable. The Meteor, the Vampire, and soon the Hunter all promised speed beyond imagination, but they lacked something the Hornet still offered: range, subtlety, and grace in flight. Jet engines roared. The Hornet sang. The Royal Navy adopted its own version, the Sea Hornet, fitted for carrier operations. It served in the Far East Fleet, patrolling the Malayan coast during the early stages of the emergency. There, in the dense humidity of 1948, the aircraft's wooden structure suffered, glue joints weakened, skins warped in tropical air. Maintenance crews labored under canvas awnings to keep them serviceable. The future, it seemed, belonged to metal and to jets. Back home, the British public saw little of these machines. Unlike the Spitfire or Lancaster, the Hornet never became an icon of victory. It appeared in no war films, inspired no propaganda posters. Yet among those who built and flew it, the pride ran deep. The aircraft embodied something characteristically British: quiet excellence without spectacle. In Parliament, a 1947 debate on aircraft research funding briefly touched on the Hornet program. One MP from Hertfordshire remarked, "If one wishes to see what our engineers achieved under constraint, one need only look to the Hornet, the last propeller aircraft to outfly a jet." It was a statement of both pride and irony, for by then de Havilland had already begun work on the Comet, the world's first jet airliner. The designer himself, Frank Halford, moved on to turbine work. His next project, the Goblin jet engine, would power the Vampire, the very aircraft that rendered his contra-rotating masterpiece obsolete. When asked about this in a later interview with Flight magazine, he replied simply, "Progress has its own logic. One builds what is needed next." By the decade's end, the Hornet had become a rarity, a machine revered by test pilots, studied by engineers, and largely unseen by the public. Yet in its brief post-war service, it represented something profound, the exact moment Britain bridged its past and its future, when the craftsman's propeller gave way, gracefully, to the scientist's jet. And though history would remember the jet age as the symbol of modernity, it was the Hornet that closed the book on the age of flight as art. By 1949, the skies over Britain had changed beyond recognition. The propeller's rhythmic pulse had given way to the clean whistle of turbines. On airfields that once echoed with the rumble of Merlins, now stood aircraft with sleek, swept wings: the Vampire, Venom, and the early Canberras. The men who had built and flown the Hornet watched this transformation with a kind of quiet pride tinged with melancholy. They had completed one story, only to begin another. In engineering terms, the Hornet's greatest gift lay not in its speed, but in its precision. The contra-rotating gearbox, that impossible mechanism Halford had once been told would never function, under combat stress became a study model for vibration control, airflow balance, and torque cancellation. At Rolls-Royce in Derby and Napier in Acton, those same lessons informed early turboprop research. Even as the nation's design centers turned toward jet propulsion, the habits learned from the Hornet, obsessive balancing, clean aerodynamic lines, and the marriage of lightness with power endured. The Royal Aircraft Establishment at Farnborough published its technical review of the program in early 1950. The report concluded with a single line of understated satisfaction. The contra-rotating air screw achieved stability of thrust under full load conditions. No further development necessary. It was a modest ending for what had once been a radical experiment. The final page in Britain's mastery of the piston era. Meanwhile, the aircraft themselves served briefly in frontline squadrons. No 19, no 41, and no 65 RAF among them before being relegated to secondary duties. In the Far East, Sea Hornets flew photo reconnaissance missions over the Malayan jungles, their engines running flawlessly in the hot, humid air. Maintenance reports from the Fleet Air Arm recorded minimal gearbox failures, a testament to the precision of British workmanship, even in tropical service. In 1951, when the last production Hornet left the Hatfield line, few took notice. Britain's aviation press was already captivated by jets, the Vickers Valiant, the de Havilland Comet, and the coming promise of supersonic flight. Yet among engineers, there was an awareness that something irreplaceable had ended. The Hornet had marked not only the technical limit of the propeller, but also the end of an age when individual designers could shape entire machines with pencil, slide rule, and instinct. Frank Halford, now deeply involved in turbine design, remained characteristically reserved. When later asked what he thought of the Hornet's legacy, he answered, "It did what it was meant to do. It proved that precision could win." Those who worked with him recalled a man uninterested in fame, absorbed entirely by the quiet perfection of mechanical truth. The Imperial War Museum would later acquire